Okay, now we're going to sort of look at the commonalities between these integral theorems that we've been looking at. So first off, we already talked somewhat about how Green's theorem and Stoke's theorem are basically the same thing. The only sort of difference between these two here is that in the first one, we're thinking of R as being a subset of the plane, and in the other one here, we're thinking of R as being some two-dimensional subset of R3, so in other words, a surface. And now if we look at Green's theorem, let's see, so this is for computing flux, so we're looking at the normal component, so this is a flux integral, and it's related to the divergence of f on the other side. And in 3 dimensions, same thing. If we look at the normal component of the vector field coming across through the surface transversely, that's going to be how we compute the flux, and it's related to the divergence of the vector field inside the solid object itself. Okay, so in this video and the next one, or in the next two actually, we're going to make these analogies a little bit more precise. But first, wait, there's more, right? So we also have the fundamental theorem of line integrals. And so for this one, we know that f at the end point of the curve minus f at the start point of a curve is going to be equal to the integral over the curve of the gradient of f dot dc, right? And if we break, and then when we studied the fundamental theorem of line integrals, we also saw that this is a generalized form of, in fact, the fundamental theorem of calculus, which when you get right down to it and unpack all the parameterizations and everything, all of this is proved using the fundamental theorem of calculus. We've mostly skipped over that because I haven't been covering the proof so much, but that's what it is. And so if we wrote the integral from a to b as being the integral over this little one-dimensional set, the integral from a to b, then this is f prime of x dx. Okay, but these are all the same thing. We have on the one hand, we've got some derivative of the thing we're interested in, and then on the other hand, we are looking at the boundary of the region that we have. So derivative, and then over here the boundary of the interval AB is just the 2 points A and B. And so in fact we can make that a little bit more precise as well. Suppose we let our vector field be, and now we're going to talk about a one-dimensional vector field, which normally we don't do, we just call it a function, but here I'm going to write it looking like a vector field, so it's only got an I component. So that's my way of saying that this is like an ordered tuple where the first thing in there is this and there's nothing afterwards. So usually we don't write those brackets, right? Well, so then if we're looking at this interval from A to B, the outward orientation on the boundary of this set, which is just the points A and B, would be that we should have the normal at A is going to be pointing, well, let's see, here's R, here's our interval from A to B, so the unit outward normal vector is pointing this way and this way, and each of those is length 1. So on the right hand side it's I, and on the left hand side it's minus I. Yeah, so there's our unit outward normal vector for this trivial sort of one-dimensional case. Alrighty, so then let's see, so then if I look at f of b minus f of a, what is that really? That's f of b I dotted with I at that end, because that's and then we've got plus f of a I dotted with the normal vector minus I at that end. So that would be the fully expanded form of capital F A dot n plus capital F B dot n. Okay, and so the moral of the story is that I can add to this list f of a dot n plus f of b dot n, and that's equal to the integral over the interval from a to b of the divergence of this one-dimensional vector field with respect to x, which is our length element. I could use dx or ds. They coincide in this little simple case. And so this thing that you see over here on the left-hand side, you should think of this as being a zero-dimensional integral. We're adding it up, but we're actually, instead of adding it up over all infinitely many points in some interval, we're just adding it up over a set of 2. Okay, the main point, and we'll make this precise in the next 2 clips, is that all forms say the same basic thing. They're saying that the integral of the operator del dot acting on a field. So the integral of del dot field over a region equals the integral of the field component over the boundary of the region. And so when I say component here, I don't mean like the x component or y component or z component. I mean the tangential or normal component, as makes sense by the set that you're looking at.